Good morning class. In the last class we did the ADT called list, and to just recap, what is the ADT list? List is a sequence of items, unordered items for that matter, and then we defined a whole lot of operations on lists. We also looked at the implementation of lists. What did we talk about? We talked about two different implementations, although I showed you only the linked list implementation, both the array and the linked list, and I showed you a linked list implementation of the list. I encourage you to do the array implementation of the list. Now I just have some problems over here. I'd like you to work on storing sets. I gave you an example of storing sets using lists, and basically you want to perform operations on set union, intersection, and set A minus set B. I also want you to look at another application of lists is what we call infinite precision arithmetic. That is, if you want to do, let's say you have a 64-bit machine and you want higher precision than 64-bit, then you can use the list as a structure to perform arithmetic on it. So basically what you do is, what we are talking about is in the list here, your A1, A2, AN up to AN corresponds to different parts of a given number, and then you define operations to perform arithmetic operations on this number represented as a list of elements. What I mean by that is your the numbers represented in parts in terms of A1, A2, AN, and you want to perform arithmetic operations on them. So I'd like you to try these problems. I also have a few assignment problems. We talked about this a little in the last class, but I would like you to write a function to remove duplicates in a given list using only list operations, and basically a function which takes a list and returns the purge list. And I also want you to convert a given unordered list into an ordered list. Again, it should be done in place. Okay, so I would like you to do these two problems on lists. Now next, what we're going to talk about is a different type of ADT called a stack. What is a stack now? A stack is also a list. Also a list, but it has a fundamental difference. It's a special type of list ADT, and the difference in the stack is that it operates on this principles of what is called last in, first out. What is the meaning of this? That is, the last element which enters into the list is removed first. This is called a stack. Now let me give you some example. When you are putting books on your table, then you put the topmost, the most recent book will be the topmost book, and then when you remove, for example, if you want to remove this particular book, you remove the top two books before you can remove this book. Another example, let us talk about plates that are stacked in a cupboard. Okay, so you put your plates over here and like this, and you remove the topmost plate. The most recent plate is what is first removed. If you want to remove the third plate from the top here, you have to remove the first two before you can remove the third plate. Okay, so stack has a lot of nice applications, and we will talk about a specific application of stack. The operations that are supported by the stack are: you can push, you can pop, and you can find what is the topmost element in the stack. You can also check whether the given stack is empty or not. Okay, so these are the four operations that are normally supported by the stack. And now, since stack is a special type of list, I want to show you one example here where, since now the way we look at it is, I have already implemented the list ADT, and since I have already implemented the list ADT, I would like that I would like to use the list itself to represent a stack. So how do I go about doing that? The way I would do that is, since the list ADT has been, you've already debugged it, you have tested it, and so on and so forth. So what we could do is, we could use the list ADT itself as a stack. So how would I do that then? Then what I will do is, I will restrict my operation. So what I will say is the push operation. So within I can write an ADT stack here and say that stack or a class stack, and I will say that I have L which is of type list, which I have already defined. Okay? This is my private data. Then I will define a set of operations on stack. And what are the operations that I want? I want push, I want pop, I want top, and then I want empty. Okay. So, what will I do for push now? I will say push x comma, what do I do? L dot first. What does L dot first return? It returns the position, right, of the first element. So, insert at the first position. Then I can pop L dot first, because this was the most recent element that was inserted. Okay. Top will also give me L dot first. Pop will be L dot first comma L dot delete L dot first. Okay. And top is L dot first, and okay, what it should be? Empty is if the L dot first equals L dot end, then I can say that the stack is empty. So, what have we done in this process here now? We have all these operations over here, right, and sorry, this should be retrieve of top should be L dot, I have written it over here, retrieve of L dot first. Okay. This is what how we would implement all these 4 operations of the stack using a list. Okay. So, you can use the list ADT in its present form, which you have implemented well, as a stack ADT and perform the 4 operations which are required for the stack. All right. Now, what we will do is, so once I have this, so one of the things that I am trying to encourage you to do is that basically that if I already have a ADT which is implemented, I try to reuse that abstract data type as much as possible, because why do I want to do that? The primary reason I want to do that is the list ADT which we implemented in the last class is, let us say, nicely debugged. Okay, there are no errors in it. So, what I will do is I will quickly define a stack using the list, and then I will use the stack to perform various operations. What I am going to do right now is I am going to give you one application of stacks, and then we will look at the implementation of the stack a little later. Let us say I want to convert an infix expression to a postfix expression. To postfix. Let us see why we want to do this. Okay. Let us say I have an expression which is given like this. Something like this. Let us say I have given an expression like this: a minus b star c plus d star f plus c by d. Okay. And suppose we know that star and slash have higher precedence than minus and plus, and the all operators are left associative. Okay. What do we mean by this is that a minus b plus c is equal to a minus b plus c rather than a minus of b plus c. Okay. That is, we assume that all the operators associate to the left. That is the meaning of it. If I am given an expression like this, I do not know whether I have to perform a minus b plus c, or should I perform a minus of b plus c. Okay? That is where the associativity matters. What is interesting is that when I am given an expression like this and I do not know the associativity of the operators, it is difficult to evaluate this expression. Okay? So, what is done is, given a particular expression, the expression is converted to a form called the postfix expression. Okay? So, let us see what this postfix expression is all about. Let me just take only a partial expression, a minus b star c, let us say. This will be written as a b c star minus. What is the meaning of it? We take the topmost operator, okay, then you come to the next operator, and the next one is still an operator. So, you push it somewhere, take the next operator, again you use a stack for this, then you take then you find on the top there are two operators over here, two operands over here, you compute this b star c. The idea is that what happens is that the operator associate with the, it is a binary operator, associates with the nearest operands that are there. So, what is nice is the advantage of this expression, when you write it in this form, there is no issue about the evaluation. Why is there no issue about the evaluation? Because you look at the operator, you just, for example, if I keep moving along this, as soon as I come across the first operator, all that I will do is I will take this operator, operate it on these two operands, get the result and put it there, and let me call it d. Then I have a, d and minus. Okay. Then it means I have to find, I must do a minus d. Okay. So, there is absolutely no ambiguity when a given expression is given in postfix the order of the operations. Whereas, if I give the expression in this form, which is called infix, I do not know whether I must perform a minus b star c. I do not know the associativity, I do not know the precedence of the operators. Everything is subsumed in the postfix expression. Given a postfix expression, all that I have to do is I traverse that postfix expression from left to right. As soon as I come across an operator, I take the nearest two operands, perform the computation, then you can put it back on stack. There is a way of evaluating again using the stack. Then once I get the result, I have a, d and minus on the particular stack. Then again, when I traverse this, for example, next I see another operand over here, and as soon as I see this, I see another operator over here, then I take the most nearest two operands, perform this operation, and I get the result. So, the evaluation of expressions is normally done using the postfix expression. You take an infix expression is very convenient for us to write, but what we do is we take the infix expression, convert the infix expression to a postfix expression, and then perform the computation. Okay. So, now what I am going to show you is the evaluation also can be done using stacks, but we will take one application. We will look at conversion of infix to postfix using the stack. Let us see how this gets done. Okay. So, what is it done here? When an operand is read, that is, I am getting this expression here. As soon as I find an operand, what am I going to do? I am just going to simply place it on the output. Then when an operator is read, what do? I take this operator. So, that means let us go back to this particular expression. Take this expression, now I see an operand, I put it, this is my output, this is my input. Okay. Then what do? I put it on the, I put it to the output. When an operator is read, what I do is, I look at the element, I have a stack here, right now my stack is empty, look at the element which is there on the top of the stack. Okay. If the top of the stack has higher precedence, then I keep popping all the elements from the top of the stack. Okay. So, this part is not there because it is empty. Okay. So, what am I going to do? I am going to simply stack the current operator. I put minus on it. Then I have B here. then what do I see? Then I have another, I see another operator over here. So now I look at the top of the stack, there is a minus sign here, minus sign has lower precedence. So what I do? I just simply stack star also onto it. Then again I see an operand, move it to the output. Next what do I see? I see a plus. When I see a plus, what I do is the following. I look at the content on the top of the stack. So star is the content on the top of the stack. Okay. So since star is the content on the top of the stack, I output, and star has higher precedence. So the precedence is like this, star comma slash and plus comma minus, and of course above this you have the brackets. Okay. So what I do is I pop the star, then once since I pop the star, what do I have? I only have minus on top of the stack. What is the current operator that I am looking at? Plus. Now clearly plus and minus have same precedence. So what I do? I also pop the minus. Then what I do? I put this plus over here onto the stack and we proceed. Okay. This is how this whole operation goes about. Alright. So basically this is what we do, and now I have done up till this part of the expression. Now let us look at the next one. What do I have now? The plus is gone, it is gone to the stack. I get D, I push this onto the stack. Then what do I have? I have a left bracket. I put the left bracket also onto the stack. Then what do I have? I have F, right. Then I put the plus on the stack. Then I have CD. Then I have the slash over here. I compare with what is there, put it on the top of the stack. Okay. Then what happens? I come across the right bracket. Okay. So as soon as I come across the right bracket, I pop everything off until I see the left bracket. That means I put the slash here, I put the plus here, and then what do? I have come to the end of the expression, star and plus. Okay. So this is how I complete the expression. Okay. So this is the conversion from infix to postfix. So what have we done? We took the infix expression, then we converted it to a postfix expression using a stack. Now let us see if it will give us a evaluation correctly. What did I say? I just keep this as it is. Then as soon as I see an operator, I find the nearest two operands and compute the computation. Let me call this B prime. That is, I have computed these two, and let us say this result is B prime. Then what do I have? I have AB minus. Now clearly there are two operators and there are two operands and there is an operator. So I compute this. Let me call this A prime. So what do I have now? I have already computed this. Now I have D, F, C, D slash plus star plus. So what do I do now? I keep moving from left. This is computed. Let me call it C prime. Then I have F C prime, okay, D A prime. So what do? I compute this. Let me call this F prime. So I have A prime, D, F prime plus, and sorry, plus is already gone. D prime plus, yeah, F plus CD, right. So CD, let me call this C prime, yeah, plus is already gone. I already computed the sum over here, and then I have a star over here and a minus. So next what do? I compute A prime, DF prime, let me call it D prime, after the multiplication, because I see the multiplication here, multiply these two, put the result in D prime, I have a minus, and now finally get the result, okay, which is essentially what so basically what it tells me is, if I follow the rules of arithmetic for a postfix expression, what does the rule say? I take whenever I see an operator, I take the nearest two operands, perform the computation and store it. Then what happens? That becomes a new operand now, B prime. then A times B prime, A and B prime, and there is an operator here minus. So I compute the difference of A and B prime, again put it back on top. So then I call it an A prime. Then what happens? I have D, E, F, C, D. Okay, I just put them all together. Then I see a slash. When I see a slash, what do? I take the nearest two operands, okay, divide them. Here the operator is slash, so I divide C by D. I call it C prime. Okay, then I have A prime, D, F, C prime. Then what happens? I have F and C prime. So this is this part. So I add them. Then what do I have? A prime, D, F prime, let me call it. Then D, F prime star. This star is here. So I perform this computation, and after, because that's the first operator that I am saying, I take the nearest two operands, perform the computation. Then finally I'll get a new let me call it, I get a new operand called D prime and A prime D prime, and I subtract one from the other, and the postfix expression can be evaluated. So clearly what it tells me is, using the algorithm that I have given here, the conversion to infix to postfix is correct. Okay. So basically I can use a stack to take this input, convert it to postfix. So what are we doing when we are doing this? We are taking all the operators, stacking the operators, including brackets. Okay. And when do we pop? As soon as we come across an operator which has lower precedence than what is there on the stack, I pop all the operators from the stack which have higher precedence and the operators which have the same precedence too, and put this operator onto the stack. That is exactly what we did. Let me illustrate this with a pictorial example again. So let us say we have the same, I have the same, almost the same expression which I have already gone through over here. I never realized it. Okay, this is the same expression that is there, and here is a pictorial description of what is exactly happening. Stack the plus, this is the top of the stack, then A is kept outside, and then you get ABC, then you put ABC star, pop this, and so on. So this is how your output gets generated. As soon as you see a bracket, you just push everything out. Okay. So this is how you convert and invert. So basically this is the first thing. What is it? The stack is a stack of operators. So what's happening now? Plus and star are stacked. Then as soon as the next plus comes, you pop both plus and star, just as I already told you, and then you see the bracket, you put the bracket on top of the stack, then repeat the same process again. Okay. So this is essentially how stack can be used. Now let us look at the implementation of the stack, and what are the operations. Now I am looking at a separate implementation. Let us say that I am not going to use the list, I want to implement my own stack. Before that, what are the time complexity of these operations? When look at L dot insert, L dot delete, L dot retrieve, what will be the time complexity of all of this? If you can say, if you look at it depends upon the kind of implementation. If the implementation is a linked list, does not matter. In this particular case, if I am inserting at the first, all these operations can also be done in order one time, even when I am using the list. Okay. But we can do a cleaner implementation. We can implement a stack. So since I am in this particular example, I am using the operators. I have created a stack which is I am using an array implementation here. This is your static array. So basically the stack size here. So you would also like to have a stack full perhaps. So I create, or you resize the stack. If you want it to be transparent, you can always resize the stack. Then you create an empty stack, which is make null. Then you push a character onto the stack. Character pop returns the topmost element on the stack. Pop deletes the element from the top of the stack. Empty tells you when the stack is empty. Okay. So and here is how the various operations can be performed. And basically what is interesting is all the operations here. If you look at this, if you look at the analysis of this, I want you to go through this over here. Make null, it simply creates the top of stack to be stack size. Then we are just pushing from the stack. What are we doing? Here in push, for example, I am making the stack size the top of stack. Initially it maps to the largest element in the array, possible in the array, largest index possible in the array. Then what do? We decrement the top of stack and then push the element there. and then when we, so this is again an order 1 operation, if you notice. This is an order 1 operation, this is an order 1 operation. Then when then what are we doing? If the top of stack is less than stack size, is returning the top of the stack. That means otherwise what's happening, you're performing a top operation with no elements on the stack. That's the meaning of this return 0 over here. Then if top of stack greater than stack size, return 0 again. Otherwise what are we doing? You're popping the particular element on the stack. That is, you're trying to pop more elements than there are. Otherwise if there is an element on the stack, it pops this. Then if stack is empty, is greater than top of stack, top of stack is greater than stack size, then you say return greater than or equal to stack size, then you say that the stack is empty. So the time complexity of all the operations that are performed on stacks using arrays is order 1. Now what I want you to do is, I want you to go back and implement the stack. I've given you a array implementation of stacks. I want you to do a linked list implementation of stacks, and of stacks, and all operations must cost only order 1. Okay. So I want you to go back and experiment with this. Now what I will do is, I will just close this with some applications. Now I want you to do this. Right now when we looked at operations, we only looked at left associative operators. What happens if an operator associates to the right? Let me give you an example. If I have an example like this, x to the power of y to the power of z, then what is this? This is essentially y to the power of z whole x to the power of. Okay. So I want you to think of this. How would you use the stack? How would you modify the infix to postfix converter if you work with operators which are right associative? Another function that I would like you to write is determine whether the parentheses are balanced in a C program. I want you to look at all these types of parentheses. I also want you to write a function that uses a stack, we already talked about it, to evaluate a postfix expression.